We'll be looking at covalent bonds and the energy level and electron configuration of atoms that allow them to form these covalent bonds. So over here, I have my periodic table, and the elements in the periodic table are arranged by the smallest atom to the largest atom. The atom size increases going across the periodic table from left to right. And by atom size, I mean the number of protons and neutrons present in the nucleus increases going across the periodic table. But as we've seen in our previous video, the number of electron is the same as the number of protons in atoms. Therefore, the number of electron also increases going across the periodic table. Electrons don't just orbit around the nucleus in a random fashion, but they fill specific energy levels. And in the periodic table, the elements have already been arranged based on the energy level that their electron fill. So the first row is our first electron energy level. The second row is the second level. So this is first, second, and so on, all the way down to the end of the periodic table. These energy levels are often called shells, and they are made up of subshells. The way I like to think about it is rows of seats in planes. In planes, you can find different types of rows of seats. In some planes, you only have 2 seats per row. Sometimes when you have bigger planes, you will have 3 seats in the middle, or even 4 seats if it's a very big plane. And this difference in how many seats your row has is the subshells of a energy level. So the row is your energy level. So this is, for example, your first energy level. And the number of seats is the type of subshell of your energy level. In chemistry, we have given them different letters to differentiate the different types of subshells. And the periodic table has arranged them again very neatly into blocks. The S subshell is this block on the far left. P subshells are found in this block on the far right. In the center, we have the D block. And down at the bottom, we have the F block. In biology, we don't have to concern ourselves with the D and F block, thankfully, because we tend to stop just about here in terms of elements that we concern ourselves with. And the other thing that is important to remember is that helium over here is our lovely exception to the rule. Although it has been placed to the far right, just on top of all the P block elements, is actually part of the S block. So that's something that you need to keep an eye out for. Now, these subshells have different names, and they have different numbers of orbitals. Orbitals are our seats in the previous analogy. So the S block only has a single orbital. The P block has 3 orbitals. Now, the reason why we are so interested in all these energy levels and different number of seats for electrons is because we are interested to know how many electrons are present in the outermost layers of elements, because those electrons are incredibly important. They're called valence electron, and they're what are able to interact with other atoms and form bonds and create larger molecules. So let's take carbon as our guinea pig, and let's try and figure out how many electrons it has in its outermost shell. So Carbon has 6 protons and 6 electrons. And before we can just rush into filling up the different orbitals, we first need to pay attention to a couple of rules that we have to follow. The first rule is the Pauli exclusion principle, which states that no more than 2 electrons can occupy the same orbital, and that 2 electrons in the same orbital must have opposite spin. So, what this means is that the first part is pretty straightforward. We can only have 2 electrons in an orbital. And the second part talks about this opposite spin, which for biology, we don't really have to worry too much about it. It, for us, is more of a notation format than anything else. When we represent electrons in orbitals, we draw them as arrows, either pointing up or pointing down. And what this second statement is telling us is that we're not able to draw 2 electrons facing the same direction, either both up or both down. So this is the only way that we're able to draw the electrons in our orbitals. And the other rule that we need to keep in mind is the Hans rule, which states that electron fills orbital of the same energy by occupying each orbital singularly with the same spin before pairing up. So when we put all this information together, we can start adding our electrons in our orbitals. We'll start from the first shell, and we can add our first electron facing up, and then we can add our second electron facing down in the same energy shell. That way we've been mindful of this law. And then for our next electrons, we'll move on to the second shell. In our first subshell, we'll put the third electron. And then following Hans rule, we have to move on to the P subshell, where we add our fourth, then fifth, and our final electron. Now, if we had a bigger atom like oxygen, which has 8 electrons, then we can go back into our second S subshell and start filling that up and moving on onto our P block. But because carbon only has 6 electrons, this is where we stop. So we can now see that in the outermost shell, which is this over here, we have 4 electrons. Now, these electrons are not paired up. Atoms like to have their orbitals completely filled, like for the first shell, and that's because when their orbitals is fully filled, it helps the atom be more stable and have a lower energy level. And so in order for carbon to be able to fill these orbitals, it will start forming bonds with other atoms. One of the bonds that it can form is a covalent bond. Covalent bonds are 2 atoms sharing a pair of electrons to achieve a more stable outer electron shell. So, as we mentioned already, carbon has 4 electrons in its outer shell, and it wants to reach a total of 8 electrons in its outer shell. So the way that it does that is sharing electrons with other atoms, as we can see here. And by doing so, it not only helps carbon reaching a fuller outer shell electron configuration, but it also helps the other atoms as well, reaching a fuller outer shell electron configuration. The atoms that I've chosen here are nitrogen, phosphorus, hydrogen, and oxygen. And the only reason why I chose them is because these are going to be the most common elements we're going to see in biology, especially in this course. So it's quite nice to start getting to know them. Multiple covalent bonds can also be formed between 2 single atoms. For example, over here, we have 2 carbon atoms, and they can form either a single covalent bond, a double covalent bond, or even a triple covalent bond. I hope that this video was helpful in giving you a bit of an overview of covalent bonds and electron configurations. In the next video, we'll be looking at ions and ionic bonding. Thank you for watching, and I'll see you next time.